Today we will learn how to balance chemical reactions. Our question of the day is, what is the difference between a coefficient and a subscript? If we consider the law of conservation, in order to balance equations, we can only change the coefficients. This changes the number of molecules or moles of the substance, but not the substance itself. For example, we can change H2O to 2H2O. On the other hand, we cannot change the subscripts in a chemical formula. Changing H2O into H2O2 for the sake of balancing would turn water into hydrogen peroxide and would result in a different reaction. In the reaction below, the reactants, hydrogen and oxygen, combine to form water. We know that this reaction is not balanced because on the left we have 2 oxygens, but on the right we only have 1. So in this reaction, an oxygen atom would be destroyed. Let's use this as practice to balance equations. First, let's draw vertical lines on both sides of the arrow to separate our products from our reactants. In our example, step 1 looks like this. Now, for step 2, we will list all of the elements in the equation between these 2 vertical lines. If we have a polyatomic ion that does not get decomposed or altered, we can write the entire polyatomic ion between the vertical lines. Let's write hydrogen and oxygen below our arrow. Now, count how many atoms of each element you have on both sides of the equation. For our reactants, you can see we have 2 hydrogen atoms and we have 2 oxygen atoms. On the product side, we have 2 hydrogen atoms and we have 1 oxygen. Now, let's alter our coefficients and keep updating the chart below the equation until there is the same number of atoms of each element on each side of the equation. Notice how, although the hydrogens are the same, the oxygens are not. So, in order to make the oxygens the same, we need 2 oxygens on the right side, or in our products. So, we need to change the coefficient in front of water to 2. However, when we do this, we now go from having 2 hydrogens to having 4. This means that the equation is still not balanced. In order to balance it, we need to update the number of hydrogens on the reactant side to 4. To do this, we will need to double the number of hydrogens. Now that we have the same number of hydrogens and the same number of oxygens on both sides of our reaction, we are done balancing. Remember, when you have no coefficient written, there is an imaginary 1. Just like in math, if you have a variable with no coefficient, then the coefficient is 1. Now pause the video and try the show what you know questions. For the first example, we have iron and chlorine being combined to form iron chloride. This is an example of a synthesis reaction because iron combines with chlorine to form iron chloride. Now, let's split up our products and reactants. On both sides, we have iron as well as chlorine. On the left, we have a single atom of iron and 2 atoms of chlorine. On the right, we have 1 atom of iron and 3 atoms of chlorine. Notice how there's more chlorine on the right than the left, so let's balance that first. The GCF of 2 and 3 is 6, so to make that happen, we're going to need 2 iron chlorides on the right and 3 chlorines on the left. We now have 2 irons in our products. So, in order to balance this out, we need to increase the number of irons in our reactants to 2, so we need to double the number of FEs. Now, let's consider nitrogen and hydrogen combining to form ammonia. This would also be a synthesis reaction. Now let's look at the number of nitrogens and hydrogens on each side. The reactants have 2 of each, and the products have 1 nitrogen and 3 hydrogens. To make the number of nitrogens the same on both sides, we would need to double the amount of ammonia. That changes the amount of hydrogens as well to 6. So in order to balance the hydrogens, we need to triple the number of hydrogen molecules. In the third example, aluminum and hydrogen trade places to make a new compound, so this is a single replacement reaction. Once again, we look at both products and reactants to find the number of atoms of each element: aluminum, hydrogen, and chlorine. On the reactant side, we have 1 of each, and on the product side, we have 1 aluminum, 2 hydrogens, and 3 chlorines. Looking at both sides, we can see that the chlorines are not balanced, so to balance those, we need to have 3 HCl's on the left, which results in 3 hydrogens. However, now the hydrogen is definitely not balanced, so the least common multiple of 2 and 3 is 6, which means we need 6 HCl's and 3 H2s. That changes the number of chlorines to 6, and now we need to balance the chlorines. So we need to have 6 on the right. We need to double the AlCl3s. This changes the aluminums to 2, and so to balance that, we put 2 aluminums on the left. Notice how the fourth example has 2 compounds on the left and 2 on the right, with the only thing changing being that the anions switch places. That means this is a double replacement reaction. We start off with 1 calcium on each side, 2 nitrates on the left and 1 on the right, 2 hydrogens on the left and 1 on the right, as well as a sulfate on both sides. In order to balance this, we will double the number of nitric acids to make 2 nitrates and 2 hydrogens, and now our reaction is balanced. This was made so much easier by the fact that we kept the polyatomic ions together. In example 5, we have one thing being broken down into 2 different things, so that makes this a decomposition reaction. Since the polyatomic ions do not stay together, we write the individual elements when we balance. On the product side, we have 2 nitrogens, 2 hydrogens, and an oxygen, and on the reactant side, we have 2 nitrogens, 4 hydrogens, and 2 oxygens. So to balance this, we will need to double the number of H2O's, giving us 4 hydrogens and 2 oxygens. Looking at example 6, the copper and silver trade places. Since only 1 new compound is formed, this is a single replacement reaction. On the reactant side, we have 1 copper, 1 silver, and 1 polyatomic ion. On the right, we have 1 copper, 1 polyatomic ion, and 1 silver. That means this is actually already balanced, and we don't have to add any coefficients. In the next example, we have a compound being broken up into 2 substances, a new compound and an element. That makes this decomposition. Since the polyatomic does not stay together, when we balance, we need to consider each atom separately, meaning there is 1 calcium, 2 chlorines, and 6 oxygens on the reactant side, and there is 1 calcium, 2 chlorines, and 2 oxygens on the reactant side. In order to balance this out, the least common multiple of 2 and 6 is 6, so we need 6 oxygens, which we can achieve by tripling the number of oxygen molecules. For the last example, we have nickel and aluminum trading off their polyatomic ion partners. Since 2 new compounds are formed, this is a double replacement reaction. The polyatomic ions stay together, so when we balance, on the reactant side we have 1 nickel, 1 carbonate, 1 aluminum, and 3 hydroxides. On the product side, we have 1 nickel, 2 hydroxides, 2 aluminums, and 3 carbonates. I'm going to choose to start by balancing the aluminums, so we need 2 aluminum hydroxides, which changes the number of hydroxides from 3 to 6. Now let's balance the hydroxides, so In order to get 6 on the right, we will need 3 nickel hydroxides, which changes the amount of nickel to 3. To balance this nickel, we then need to triple the number of nickel carbonates, which also triples the number of carbonate. Now we have the same number on each side. Our reaction is balanced.